Welcome to our webinar series about motor protection with Siemens SIPROTEC 5 protection relays. My name is Edward Strasser. I'm the head of the Channel Partner Program of Siemens Electrification and Automation in the 26-country region managed from Siemens Austria. I'm happy to be your moderator for this webinar series, which offers valuable information for operators and maintenance engineers, for design and protection engineers, and for those preparing technical specifications for motor protection projects. Our expert for today's event is Klaus Wagner. Klaus is a specialist for motor protection with over 25 years of protection experience in various protection technologies here at Siemens. Why are we doing this webinar? First of all, we received many requests for further details following our annual channel partner meeting in the Austrian region, our VAR Grid Plus Partner Day last fall. And as we began preparations for these webinars, we realized there was an even larger audience for the information we wanted to offer. And so we're happy and very pleased to welcome customers, partners, and design engineers from not only our 26-country region, but in fact from across all of Europe and also globally. I keep mentioning partners. And by this I mean integration companies, EPCs, switchgear manufacturers, and similar companies who use the product portfolio of Siemens Electrification and Automation in their own customer projects. If you're not yet a partner, but this description fits to you, please talk to your local Siemens team about our VAR Grid Plus partner program. For today, since we always get this question, yes, we will be recording today's webinar. That is because we want to offer it later to further participants on demand. We're looking forward to all of your questions, and you can enter them in the upper right-hand side of your screen, also next to a chat box. That means you can give us questions live. We're looking forward to all of them, and we'll answer as many as we can at the end. But you can also chat with our experts during the webinar for spontaneous requests. Now about today's webinar. I first have asked Klaus to introduce a little bit of the SIPROTEC 5 portfolio of protection relays so that you understand the basis, just in case you're not familiar yet. After that, we'll go into an expert discussion about the motor protection. Now, today's focus will be a basic motor protection, and there will be a second session coming up soon about advanced, more detailed motor protection activities. We did this with a focus on quality, and during a rehearsal, we recorded the practice, and it worked out so well we made the following decision. We will play for you that recording, which we have improved in order to make it nearly perfect. And during that time, we will be taking all of your questions and answering them. We'll be here in the studio with you all this time. Klaus?
I'm ready. Okay. Thank you, Edward, for the introduction. As already mentioned, before we go into the discussion about motor protection, before I show you an overview of the functionality, let me give you an idea about the benefits of SIPROTEC 5 as a whole, because motor protection is a part of SIPROTEC 5 and it benefits from the whole SIPROTEC 5 family and system features. First of all, I would like to mention Siemens has a long tradition with protection. It goes back more than 110 years, back to 1910, as you can see here on the slides, and we accompanied the market and the developments, the new features over this time, and we continue to do this, as you can see on the right-hand side of this slide. So we are working on the future, and the last bigger or more important outcomes was, for example, the process bus, which is totally now part of SIPROTEC 5, or our digital twin, which is a simulation program of our SIPROTEC 5 devices that runs the original software. I will talk about those things later in detail. especially about the digital twin. With a large installed base of protection devices, so SIPROTEC, 2.5 million roughly, then Ray-roll devices, which are also part of Siemens protection, 500,000 devices. And then we are active also with substation automation and also power quality devices. SIPROTEC 5 stands for a rugged and robust hardware. As you can see here on the slide, we have two representatives. On the left-hand side, you see the SIPROTEC 5 compact device, a 7SX800. And on the right-hand side, so this is the low-end part, let's say, of the range. And on the right-hand side, our modular devices, where we can add the modules on the upper end of the range. So SIPROTEC 5 had a focus. One of the focus was to keep or to provide maximum flexibility for the user during the whole project and during the whole lifetime. What does this mean? First, we have an expandable hardware, as you can see here. That means you can buy the device with various hardware sizes right from the beginning, but you can also add hardware modules, as you can see here on the right-hand side, during the whole lifetime of the device. During the project, if something comes up and you need more IOs, for example, you just order an expansion module. You don't need to throw away or use in another way the device and buy a new one. You just order this expansion module. So you don't need to send back the relay to the factory, and this is maximum flexibility in the hardware. Benefit for you, you can react fastly on changing requirements during the project or also during the lifetime. If the relay is in service and you want to add something or you want to place it into another place, maybe you can just upgrade the relay. And the adaptation is economic because you don't need to buy a new relay, just upgrade the existing relay by using another expansion module. And this gives you peace of mind. So what about the communication? We have plug-in modules, which are mainly for communication, most of them, but they are also for transducer inputs, voltages and currents, and also we have one module for arc protection. The installation is relatively quick and is possible also during the whole lifetime of the device. So the communication protocols can be selected in the DIXI 5. That means if you once have a piece of hardware, for example, an Ethernet module, you can select later during the whole lifetime if you want to stay with the original or initial protocol or if you want to change the protocol, maybe because newer protocols are coming up. So you have this flexibility as much as possible. All the protocols that are running on one module are always available. Benefit for you, again, you have a fast reaction on changing requirements and the system is future-proof. Let's talk about speed. We have pluggable terminals. Speed because you can pre-wire the device, or not the device, the terminals in the cubicle, which is possible if you have them on stock. And if you have a project which is time critical, you can order the device and start in the meantime with the production of the cubicle and also with the wiring and the testing of the wiring. If you have these terminals and later when the relay comes, you just exchange the terminals, click in the relay into the wiring, and then you are done. Another point, device replacement without opening of the wiring, very important. Also, this is like speed. You don't need to open the wiring and make a new commissioning afterwards. You just click out the terminals, as you see here on the picture, on the right-hand side, and you can replace the device. So there is no full commissioning procedure necessary afterwards. Why can we extract the current terminals? Because the current transformers are in these plastic terminals, in these cubicles, let's say, as you can see here. And the trick now is that we open, you see here on the right-hand side, the opening point. What we open is a voltage connection to the PCB, to the board in the relay. We do not open the secondary of the current transformer, which is very dangerous because we have always a resistor. So there's always a closed loop in this terminal, and therefore you can also extract it while on the primary side, the current is running, there's current. Okay, therefore we do not have open secondary windings of the current transformers, and you can extract it, as already said, also when the feeder is running with load. So maximum flexibility, let's talk about functions. So now we talked about the hardware, let's go to the functions. We have function points instead of fixed function options. This has at least two advantages. All the functions are available in a DIXI5 library, as you can see here on the right-hand side. These functions can be added or swapped with the actual configuration by drag and drop the functions in the DIXI program into the configuration, as you can see here on the right-hand side. So you put them into your configuration in a few seconds. Yeah? Then the function is in the configuration. And in that way, you can also swap or delete or add additional functions in a few seconds with a DIXI5. And this during the whole lifetime of the device again, so everybody can do this. And this is the big advantage. So you don't buy a relay which has fixed functions, but you are flexible for the future by adding new functions. For example, if we develop new functions, you can take the functions and put them into the device afterwards. The functions are paid by function points. That means every function has a certain value of function points or need a certain value of function points, a budget. And if you take out a function, you don't use up that budget and you can replace a function and then you use again the function points. This is the method to remain flexible over the whole lifetime, because you can swap, exchange the functions. And these function points have another benefit. On the firstly, we have a fast reaction again when we swap these functions or exchange, adapt the function as told. With the function points, you can pay for the functions right at the very end of your project when you have the relay and you start the commissioning or the testing, when it's clear which functions really need to be in the relay. Because often at the beginning you have some ideas how to make up the scheme, and then during the project there are changes. This is all no problem, you can do this in the DIXI, but when it comes finally to download the software into the relay or the configuration into the relay, then you need the function points. You pay exactly at the end and you pay exactly what you then need at that point of time. It's also here a flexibility, and of course this gives you again peace of mind. Finally, we have helping programs and tools. First, the digital twin, which is a simulation of the protection relay itself. I already mentioned there's the original software of the relay running in this digital twin. That means the behavior of that digital twin is identical with the behavior of the protection relay. So you can test your configuration before you even have the relay on your table or in the laboratory or in the workshop. And you have many more features. I will come back to that point in one of the two presentations later about motor protection. Then we have the SIPROTEC tools. It's a bundle of functions that help testing the cubical wiring, for example. After the installation, you can download the firmware, the configuration into the relay, and you can upgrade the device functionality and many other functions. I will also talk about that in one of the two sessions. And finally, I would like to mention the web UI. It's a built-in server functionality in the relays. That means you can take any web browser, go to the relay and talk with the relay. You see what the relay produces you on your screen. And here you can change settings. You can get process data. You can have much more functionality. Also about that, I will talk in one of the two webinars later. But now it's enough about the general features. Let's go into the presentation of motor protection. Hello and welcome to this webinar, to this first webinar about SIPROTEC 5 motor protection. Here we present you an introduction into the topic. Why do we need motor protection? Motors are among the biggest assets in an industrial plant. If a motor gets broken, expensive and long-lasting outages could be the case. Replacement motors are often not available from the shelf, so it is essential that a motor is protected in the best possible way. We can also say the motor protection device is like an insurance to save the investment. The better the protection is, the smaller are the damages of a motor in case of failures. So, what are the typical problems with a motor that can occur? First, we have short circuits in the motor. This can damage or destroy the motor and even the driven machines, and the consequence is we have a production outage. How can SIPROTEC 5 help here? SIPROTEC 5 detects and trips fault as fast as possible and as selective as possible. That means no overfunction. Then a special stress for the motor are too high temperatures. Here we distinguish between stator and rotor. The consequence here is that the insulation ages and then the lifetime gets reduced. If we have a severe or excess heat, then we can have directly short circuit, also with the consequence of an outage of the whole production. Finally, so how can SIPROTEC 5 help here? SIPROTEC 5 has different models, temperature models, which we will discuss, to reduce the risk of overtemperature. Then bearing failures is one topic. Also bearing failure can damage or destroy the motor or the driven machines as well. Here we have a consequence, we have a production outage possibly. And finally, our SIPROTEC 5 protection relays help to protect the driven machine. There can be basically two cases: unloaded drives, then the machine gets hot, or a low jam situation where the rotor is blocked and the machine has a special stress as well as the motor in that case. Let's have a look on the protection functions for the various types of faults. Here an overview. First, let's talk about the short circuits. Here we have 2- or 3-phase short circuits. Here normally we have a short circuit protection, and this is an overcurrent protection in many cases. More sophisticated is a differential protection. Also for earth faults or single-phase faults, we have an earth fault protection. Here it depends if we have a grounded network, then normally a simple overcurrent protection for the ground is sufficient. If we have an isolated or compensated network, then we need probably a directional sensitive ground fault protection. Then the temperatures, thermal overload of the stator during operation. Here we have the stator thermal overload protection, or ANSI 49. Then for the rotor we have several cases to consider. First is a too long start of the motor. Here we have a starting time supervision, and we can also have too many starts in a row, one after the other, which harms the rotor. For this we have the restart inhibit protection function. Then we can have a loss of a phase or unbalanced voltages. Here we have a negative sequence protection or a dedicated unbalanced load protection, which has also a thermal model behind. And I put also under voltage in this category, because if the voltage is too low, then it might be that the motor cannot start up at all. In this case, it does not make sense to try it as long as possible until the maximum temperature has been reached. So the under voltage protection in such a case trips right from the beginning, so that the stator, especially the rotor, does not get a high thermal stress. Then we can have an increased load situation. Some chunks of load, coal or whatever, gets blocked, for example, or blocks the machine, or other overload situations where we have a jump of the load current. For this we have a low jam protection. And The opposite, if there is no load in the driven machine, this can sometimes also endanger this driven machine, a pump or a compressor, for example. Here we can use an undercurrent protection function or look at a minimum threshold for the active power, so under power protection we can also say. Then for the bearings, here we just monitor the temperature on the bearings with temperature sensors. And then we have, especially for synchronous motors, some additional protection functions which prevent the synchronous motor to run asynchronously. This is the under-excitation protection on the one hand and the out-of-step protection function. And an additional function is rotor ground fault detection, for which we have also a dedicated protection function. Let's have a look on our SIPROTEC 5 motor protection devices. We see here the full range. The 7SX800 is the smallest one, our compact universal device. Then we have the 7SK82 and the 7SX82. They are both non-modular devices. That means they have 1/3 of 19 inch as a size here. And finally the SK85 or SX85, which belong to the modular devices, where we can have in a modular way an increased number of binary inputs and outputs. So all of these motor protection devices have almost all functions inside. There are only two exceptions. The first exception is if you want to apply a differential protection, we need a second current transformer, and this we have only in the 7SK85 or 7SX85, so in the modular devices. And also the special protection function for synchronous motors we have only in the modular devices, so SK85 or 7SX85. Maybe a few words about what is the difference between 7SK82 and 7SX85, respectively SK85 and 7SX85. The 7SX devices are so-called universal devices, as a difference to the 7SK devices, where we have dedicated motor protection functions inside, plus additional, we can say helping or auxiliary functions. The SX, the universal devices, they are not bound to a certain scope of functions. You could put in there whatever you like. So any combination, almost any combination is available. That means you have one device and you can use that device for all applications in the complete plant, for all applications. That means you save, for example, replacement devices on stock, because you can take just one instead of one for every device family. Okay, so let's try to classify these devices, where we apply, in which case we apply which device. I already mentioned that from the protection functions, it's more or less the same, except the differential protection and the synchronous protection of synchronous motors. So the difference is mainly in the hardware setup. To classify the motors, we can say we have small motors, and here the classification is more that we say what kind of protection functions are used, not really so much the exact size of the motor. We cannot have a hard line or border here. So we say small motors we protect only with the currents, and here preferably we can use the 7SX800 with a small hardware setup, or the 7SK82, 7SX82, the non-modular devices, and of course, if necessary, also the bigger devices with the scalable hardware. So here only current measurement, and we try to put here a range of the power of the motor. Again, this is not a strict rule, it's more a kind of observation on our side, what is used for which motors basically. Then the next bigger size is when we use a voltage transformer additionally. Here we can also use the 7SX800, it has also a voltage transformer built in, the non-modular devices and also the modular devices. So here we could say this is current plus voltage measurement. And finally, the next higher class of protection would be to apply a differential protection. Here we have just the 7SK85, 7SX85, so the modular devices for the asynchronous motors and also for the synchronous motors. For the synchronous motors, we could also think about using a 7UM85. It is the universal generator protection device, and the synchronous motor is like a synchronous generator, so this would be also suitable. But the 7UM85 has many more functions than the 7SK85 on top of that, which are especially necessary for the generator protection. So here the classification would be 2 currents for a differential protection plus a voltage probably for this kind of protection. So then we have ATEX devices. For some of our motor protection devices we have an ATEX certificate. That means they can be used for the protection of motors which are in explosive environments. For the ATEX relevant protection functions, we fulfill the SIL 1 requirements according to the IC 61508 standard. With only some dedicated devices for ATEX for motor protection, which you see here, the SK80, the 7SK82 and the 7SK85, 7UM85, but not all kinds of protection variants. We have limited this to special devices, so we have a special ordering variant for this ATEX certification. A dedicated firmware stands behind, a dedicated hardware setup, and we have also a dedicated manual to describe the speciality of setting up the protection for these ATEX relevant motors. And yeah, this is because we have to qualify or certify the devices, test the devices as it is, as a special hardware and software variant. Therefore, we have just a few devices like that. Let's have a look on some typical applications. First, the small induction motors, where we have just a current, where we measure the phase currents, and we have some protection functions. So such a motor can be switched onto, in the simplest way, directly onto the bus bar via a circuit breaker, or very often we find also contactors if the motor is started and stopped very often. Additionally, there can be sometimes a transformer in between to adapt the voltage. And also optionally, we find here RTD elements, temperature sensors, to measure the temperature on certain places in the motor. As protection functions here, we find typically an undercurrent protection to protect the driving machine, some functions which belong to the thermal functions, for example, the unbalanced load protection, the starting time supervision, the stator ground fault protection, the restart inhibit function. These are those numbers here. Then a simple overcurrent protection as a short circuit protection, and maybe a load jam protection. So if we go one step higher, then we could say, okay, let's add a voltage transformer here. Then we can have additionally the voltage based protection functions like an under voltage protection 27 or over voltage protection. And if we need a directional sensitive ground fault protection, we need also at least the V0, so the zero sequence voltage, or the 3-phase voltages. Therefore, it's also mentioned here. Additionally, motor can be started via a VSD, variable speed drive, or variable frequency drive called sometimes, to start up. And then it is switched directly onto the bus bar where the speed drive is not needed anymore. In this case, we can have these protection relays as shown here on the right hand side, SX800, SK82, or even the bigger ones here with the functions already discussed. The temperature elements can be placed typically in the stator winding, so I have as a minimum 3 temperature elements for the 3 phases of the stator windings. Then in the bearings, in each bearing one temperature element, and optionally also to measure the cooling agent, so the air or the liquid inside, or we can also sense the outside temperature, the ambient temperature. If we go one step further for a large size motor, then we have here a differential protection additionally, what you see here, the 87M. And if you want to apply more sensors, then we find typically 2 sensors for each stator winding, so for each phase, and for the bearings, and maybe additional for the cooling agent and the ambient temperature. Finally, for large synchronous motors, we have some additional equipment. So how to start first such a motor? You can switch it directly online, then it starts up in an asynchronous mode, and when the speed is reached and the excitation is activated, and then the machine runs in the synchronous mode. Or it can be started up with a VSD, variable speed drive, or also as an option a special starting transformer, an auto transformer, the so-called condor for starter, which applies several voltage levels to the motor step by step, depending on the speed the motor has. Okay, for the protection, additionally, we have here the under-excitation protection and optionally the out-of-step protection function. Both care for that the motor does not fall out of step because it's loaded too much. And we have additionally optionally a function to protect the rotor ground faults, or against rotor ground faults, the motor. Here we see a typical starting current of a motor which is switched on the bus bar directly. We have a peak, normally transient current, which is relatively short. Then we have a relatively long, slightly decreasing, quasi steady state current. And then right at the end, when the motor is almost at the nominal speed, then the starting current breaks down to the load current, the actual load current. These are the three phases we see here. And this we need to understand how we can set up the short circuit protection. Let's have a closer look here into the short circuit protection. We use first an overcurrent protection. So this is really the standard for the motor. That means I measure the three phase currents and I have some dedicated thresholds for the protection of this motor. Here we have to distinguish again the three phases. So we have a peak at the beginning here as RMS values. Then I've here the starting current, which is rather steady state, we can say. And then it falls down to the load current. So if we do not want to trip with a starting current, we have to be always higher than this starting current. And this is the big disadvantage we have with a simple overcurrent protection. If you go for that, then we can put here a threshold above the peak without any time delay. And we can put here a second threshold, which is above the steady state starting current here. For this, we need to be sure that this small peak, inrush peak, when the motor is started, will not trip the stage. Therefore, we need a short delay of this stage. On the other hand, I can set it more sensitive, so lower basically. Okay, a threshold that is just over the normal operating current does not work as such without any additional conditions, because I would trip that stage probably with a startup current, or I need to delay it so long that I wait for the complete starting time that it is more or less useless, we can say. So the differential protection is much better in that regard. For the differential protection, I need two current transformers. Here, for example, additionally to the current transformer on the line side, I have the three phase currents on the start point side. And in the relay, I make the differential protection with a special function, the 87M. This is the classical differential principle, and we see we need additionally here the current transformer in the start point, so three phase current transformers. This is the additional effort on top of the protection function which I need. What do I get from this as a reward? I have a tripping characteristic which we can show in that way. So I'm very sensitive and I'm very fast, because the normal current which I see does not disturb me. So I will not pick up on the normal current, on the starting current, on the operating current. This is all covered by the differential principle. And therefore, typically I have no time delay and I have some tolerance for the difference of the current transformers. A practical value is here 20% of the nominal current of the current transformer as a first setting. But with the motor protection, you can always test this out during the commissioning. You can make some starts and then you see how big is the influence, and maybe you can even go a little bit further down. Additionally, we could use our high set stage, which is designed to be very fast. Therefore, it has not so many additional functions for stabilization as the sensitive stage. Therefore, I would recommend to put this over the starting current here, the startup current, also with a time delay of 0. And again, this stage is a little bit faster than the other one, a couple of milliseconds, which I can save in case their fault current is really high. There's a second principle for the differential protection, and this is shown here. So I have here a window type current transformer for each phase as indicated here on the bottom. So I bring the current through this window type current transformer and backward, and here in this current transformer the two currents going in opposite direction, so the starting current or the normal load current, they cancel out each other. And therefore the protection function here is a simple overcurrent protection function. So here additionally I need this kind of current transformer, and I need additionally to have the wiring backwards, so I need to have the open start point here, bring it back. For the protection function, it's an additional overcurrent protection, or an overcurrent protection as such, to create the differential protection principle. So here the benefit is that also my tripping characteristic can be set relatively low, below the load current of the motor, and also fast, so I don't need a delay time, and I can go very sensitive because under any normal condition the two currents cancel out and I get some measurement error current, a small one. Here we also would recommend to start with 20%, and during the commissioning you can measure how big this current really is and then even go a little bit lower maybe, depending on the situation. Let's come to the thermal overload protection of the stator. So here we see the stator of a motor, and what is being mounted here is the rotor which they put into the stator at the moment. So thermal overload of a motor, we have on the one hand the function for the stator overheating during continuous operation. Then we have some functions, not only one, for the rotor. And then we can discuss about the overheating of the bearings, which we do with RTD sensors. And finally, to the overload of a motor, we can also count the overload of the plant as such, the driven machine, if it's getting empty, so an unloaded drive, for example. Let's concentrate on the stator first. What we do is we permanently calculate a temperature, so we have a thermal model which is based on the currents which we can measure here, the stator currents, and this thermal model gives us a permanent temperature calculation, as already said, with standardized per unit values. The standardized values are % of the maximum stator temperature. That means if the current is 0, then my standardized or per unit value is also 0, and the temperature of the motor is like the reference temperature, 40 degrees. If I have the maximum current in the flowing into the motor, the maximum permanently allowed current, then my temperature will reach exactly 1, and then I need to give the tripping command in that case, because I reached the maximum stator temperature. Okay, what is the sense of this model? We permanently know the temperature. Now, depending on the status, if we get an overload situation, a high current that brings us beyond the maximum threshold this here, which is allowed, then it depends on the preload situation. So if we are very close already to the maximum temperature because there was already a big current flowing, then I have a small tripping time. If there was rather small current flowing for a longer time, then I have a longer tripping time. What does this help? So if this overload situation is not permanent, but only a little bit, then I can, for example, prevent a wrong tripping or an overfunction in case I have a relatively high thermal reserve. On the other hand, if I don't have a high thermal reserve, I need to trip because otherwise the stator gets too hot. Here on the side, you see the formula how to calculate the tripping times for those who are interested. So summary for the overload protection. Before we come to the summary, maybe one word. You see, if I have a jump in the current from one static level to another static level, then the temperature will follow like an E-curve, as you see here. So on the one hand upside, or on the other hand also downwards with the temperature. So it's the same thing. What we need is the maximum current, which gives us the maximum temperature, 1, which is reached at the end. So in a steady state situation, this would be like if this is the end temperature here, then all values are dimensionless values. And to define the thermal behavior, to adapt this thermal model to the real motor, we need a couple of settings only. And this is the nominal current of the motor. This is this permissible overload factor K. This expresses at the end a multiple of the nominal current, which gives the maximum allowed current, and the time constant. The time constant is also indicated here in the curve. You see, you can get it in that way that you take the straight up to here and then go down. And you see if the time constant is long, then this temperature rise is very slow. The time constant is relatively short, then you will have a fast transition to the other temperature. So this is an important setting we need from the motor manufacturer. And we calculate this permanent thermal image because it's the best way to trace the actual situation and to not to give an overfunction in case you have a higher current flowing, and not to be too slow or have an underfunction in case the temperature is already high. Before we go to the rotor overload protection, let's have a look on the motor monitor. For the motor monitor, what is behind is a state detection of the motor. That means in each phase of the motor we know in the relay, is the motor at standstill, running, or starting up. These are the states. So we have a standstill state, we have a starting state, and we have a running state. Why do we need that? Because depending on these states, we have protection functions which are active only in that stage. And this is, for standstill, the restart inhibit function. For the starting time supervision, it's the starting state which is necessary. And in the running state, and only in the running state, our load jam protection is active. Okay, how do we find out in which state this motor is? First of all, we have a fourth stage, a kind of dynamic or intermediate state, slowdown, to handle dynamic situations of the motor. But to come from one state to the other one, we have conditions defined which are relatively clear, so that the protection relay always can see, depending on the state and these conditions, if the motor is going to the other state. I don't want to go into all these conditions. In the documentation it's here, so if you want to read that later, you have it there. Good. So this state model, again, to understand what is the state of the motor, the current state, and depending on this state, we activate several functions. Now let's come to the rotor overload protection. Here we first have a look on the two symmetrical problems. So with symmetrical currents, a too long start, a locked rotor situation maybe, or the protection against too many starts in a row. Okay, we have also, for the rotor, we have also implemented a thermal model which works similar to the one for the stator. So the goal also here is to calculate permanently the temperature, and also we get standardized per unit values, and these are maximum of the percent of the maximum rotor temperature, as with the stator overload protection. However, the data input for this model is different, of course, because it's the rotor. Here we need the number of starts of the motor from the cold state, from the warm state, and then the starting time and the starting current, for which these number of starts can be applied. Basically, this is normally the nominal start, or it's dedicatedly calculated and designed for a special load situation if it's a customized motor. Okay, here's an example for the rotor temperature. If we have a locked rotor situation and we keep the rotor locked, then you see the maximum rotor temperature goes far away. This is something like 8-9 times the maximum temperature. And what we do is we monitor this small part here between 0 and the maximum temperature permanently with this model. If we zoom in, we see we have basically 2 or 3 stages which are important. First is 1. This is the maximum temperature for the rotor that is allowed, which we get exactly from these data here. Then we have the temperature when the motor is running under nominal conditions. So this would be the warm motor state. And then we have a threshold, so the inhibit stage, which characterizes the maximum temperature from which I can start 1 time more under these standard conditions to reach the maximum temperature. So if I'm above that value, I do not allow the restart. If I'm below that value, I will allow the restart again, because then I will not exceed the maximum temperature. And from this thermal model for the rotor, we get the restart inhibit function and also an additional function called rotor overload protection. The rotor overload protection takes the temperature, the actual temperature, and if this reaches the value 1, the maximum value, then it will give a tripping command. Whereas the restart inhibit function does not allow a start of the motor if the temperature is too high. Let's have a look on the restart inhibit function. It prevents a motor from being started too often in a certain time. And we have 3 stages basically. Thermal stage, based on the thermal model I was explaining before. Then we have a counter stage. If you have some data from the motor manufacturer that says the motor cannot be started more than, for example, 3 times in 1 hour or 3 times in X hours, then we can use the counter stage and also a timer stage, which you can activate if you get motor data like you need a minimum of X minutes between each stage of the motor, or hours, for example, then we can apply the timer stage. So the counter counts how many starts can be done in a certain time, and the timer stage again counts or monitors that there is a minimum time between each start of the motor. Here's an example for the thermal stage with 3 starts in a row. So we see here the current has the starting current value, then the motor is running with a nominal current, and it's switched off, and then 2 more times here. And here we see the stator temperature, the rotor temperature going up, not the stator temperature. And what we indicate here is basically we do not have just one temperature in the rotor. This can have different values, or has different values on different locations in the stator, for example on the upper bar and the lower bar. And what we do with this thermal model is to make a kind of mean value based on the given data from the motor manufacturer, because the motor manufacturer already has included that consideration when he gives us the information I can start 3 times, for example. Okay, so when the motor is switched off, I get here this restart inhibit signal, and all the time only the motor is switched off, and this can be used to block the reclosing or the closing of the circuit breaker or the contactor, so that the motor cannot start. And I've additionally here a warning stage, which comes when the temperature, the calculated temperature, exceeds this restart limit temperature. The motor starting time supervision is another function that looks that the motor starting procedure does not take too long. We have a trimming characteristic with 2 curves, basically, one for the cold and one for the warm motor. Because normally we get also data from the motor manufacturer, similar curves as we see here for our tripping characteristics, saying, okay, for example, the locked rotor curve, if the motor has a locked rotor with a certain current, it can take a certain time from the cold state, from the warm state here, and longer from the cold state, of course. This function is only active during the motor start. It has a starting condition, and it is not just a simple inverse time curve. There's also a thermal model behind, so we integrate the current up accordingly so that the correct temperature comes out. So even with varying currents, when the current decreases, then I have a longer starting time, and this is exactly balanced out according to the thermal model which is behind here. Good. Additionally, we have a locked rotor characteristic here, the red one, which I can activate if I activate a binary input, rotor locked. And therefore, we have two more parameters, basically. The maximum tripping time, if this locked rotor situation is detected. And yeah, it starts also with the starting current, so the current for the starting detection here, basically. What is the sense of this additional faster stage? So if I know the rotor is locked, I don't want to wait until the rotor has its maximum temperature. For two reasons. First, there's a lot of stress for the insulation of the rotor. Second, if I do that, then I have to wait a long time until I can start again. So here I save basically the thermal reserve of the rotor, and I can switch off the motor, then fix the problem, and then I can start again instead of waiting for hours maybe. Okay, already said, also here we calculate the temperature. It's a temperature model behind that, and we calculate the temperature permanently when the motor is starting. Let's come to the negative sequence current. If I have a voltage unbalance or a loss of phase, so here is a loss of phase, so one fuse, for example, has tripped, then the motor sees a highly unsymmetrical voltage. That means there is also a negative sequence voltage in that system, which leads to negative sequence current, and basically I have a current that flows in and out if you put the components together here. And this negative sequence current has a very bad influence on the rotor. It heats up the rotor very fast. And here we need to trip in a fast time. Therefore, we use here a simple negative sequence overcurrent protection function, which I set to a few seconds maximum, because if this situation is there, then I can trip immediately, and I need to trip immediately. On the other hand, we can have negative sequence currents due to voltage unbalance. This is what we see here. So here there's just a tiny difference in the voltages, maybe also different angles, which brings me also a negative sequence voltage system. Now we have a relatively low negative sequence reactance or impedance of the motor, so that means a tiny voltage, a tiny negative sequence voltage system creates me a relatively high negative sequence current system. And here we need to be careful and sensitive. And what we do here for this case is to apply additionally to the definite stage, which we use for the loss of phase. Here we have also a thermal model behind to better calculate the effect of these negative sequence currents on the temperature of the rotor, what can be tolerated and when do we need to trip. Again, trip only when it's really necessary, but trip if it's necessary, we can say. This is the idea behind. So we have an unbalanced load protection in the thermal model behind, and yeah, the advantage is the motor is only tripped when the temperature limit is really reached. Tripping characteristic is like that. So inverse time, similar to the starting time supervision, a thermal model is behind, and we have a starting value. This is the maximum continuously allowed negative sequence current. So normally a couple of percent of current is allowed, like 5 to 10% maybe, where the motor manufacturer says that's okay. And if we go beyond that value, then we start calculating the temperature here. And with a maximum limit not to interfere with, for the trimming time, not to interfere with the overcurrent protection. Let's come to the load jam protection. So the load jam protection, if we remember our starting curve here, we can set below the starting current, but above the maximum expected load current. This is the idea. And yeah, with the delay time, I can be also a little bit generous, not because, this delay time is not because of this peak here, because I don't see that peak when this function is active. It is more to allow the situation to recover. For example, if you have a chunk of coal that is extremely hard and does not break immediately, maybe after a second or so, it gets broken and the whole machine runs normally again, then it's no need to stop the motor in that case. Okay, so the load jump protection detects a locked rotor situation during the normal operation, or we can also say a load jump or jump of the load current better. The criterion here is there must be a current jump, so an increased current during the running state of the motor, and this running state is important. I before said I don't see that peak because during the normal running situation of the motor, I don't see that. I don't have such peaks because they come just during the startup of the motor. And this is the trick. So this stage is especially active only when the motor is running. And then I don't care about the starting procedure because I don't see that current for this stage here. It's faster than all thermal stages. Thermal stages take many seconds normally. And here the idea is not to wait until the thermal stage trips because the rotor has become too hot. No, the idea is if we see, okay, there is something blocked that endangers the machine or the motor, then let's trip immediately. And additionally, I have a sensitive overcurrent short circuit protection during the running time of the motor because I can bring that stage here further down. So it's not necessary to have it above the starting current, but I can go with some reserve above the load current. Now I would like to show you some additional functions and tools we have in our SIPROTEC 5 devices, and especially for the motor protection that help you to make the life easier. First, motor start record. It's a slow scan record which you can start or trigger with each start of the motor. And we can bring in here the analog values like measurement values, voltages, currents, and also binary signals, for example, the state of the motor or any pickup situation, for example. It's a standard slow scan recorder function which we have implemented in all SIPROTEC 5 relays, and it's in a standard COMTRADE format, a native format. It can be displayed via SIGRA, the COMTRADE viewer from Siemens, the Web UI, SIPROTEC 5 Web UI, or any other COMTRADE viewer. The standard assignment is done already for the motor protection, so we put here the motor state in this startup recording, and also the voltages and currents if available, and also the close command of the circuit breaker or contactor. You see here XT, this is on the same time also the trigger condition to start this motor start record. What is the sense of such a motor start record? You can verify first the most important parameters during the startup, like the starting current, the starting time, the voltage breakdown, for example. But you have also a history of startups because since we use only measured values, we can store a lot of these starting records in the relay, normally hundreds of starting records. And this gives you then a history backwards, so you can compare if something looks strange, then you can compare it with the behavior in the past, the starting up behavior in the past, and then make a comparison. SIPROTEC Tools is an additional program we have, a toolbox for field tasks during the mounting of a cubicle, for example, but also during the commissioning. It's useful. It's a portable program. You don't need a Dixie 5, the engineering tool, and it's free of charge. So here we see what we can do with these SIPROTEC tools. First, hardware and wiring test. This is during the mounting in the cubicle to verify if the connections from the cubicle terminals are correctly done to the connections or to the terminals of the relay. We can upload a configuration or upload also the firmware into a device without DXI5. You can upgrade the device functionality, and you can get data from the device, download device data, process data, configuration from the device onto the PC. The idea is if someone is in the substation and does not have the DXI5, he can make use of these functions and bring the result back to the office where someone is with a DXI5, or also the other way around. Let's have a look on the hardware and wiring test. So if you start this small program, then you see in the hardware and wiring test this interface here. And the idea is the following. You see here the binary inputs, and if there is this check mark, then the binary inputs gets high. That means you can put a voltage on the cubicle terminals, and if the respective binary input gets high, then you know, okay, the wiring to that binary input is okay. If not, then you have to go and trace what's wrong with the wiring. The other way around, if we have, we can close a contact, and if we click here on these buttons, that means you can also measure on the cubicle terminals closing the contact if you have really a closed loop. So with a beeper or so, then you see, okay, this is now closed, and if you open the contact, the closed loop opens again, then you know, okay, the wiring from the two terminal points to the relay terminals is correct, and it's on this binary output, for example. Then you can inject currents and voltages. Then you see here for each phase the currents and the voltages, and we have also here a phasor diagram, so you can see if the wiring from the terminals is to the correct phase, for example, current input phase or voltage input phase. And also with a phasor diagram here, you see if there's a polarity switch, because then the phasor goes into the wrong direction. Then you can test wiring between devices, between SIPROTEC 5 devices in a cubicle. In that way, you can, for example, activate a contact on one device, and you can start this SIPROTEC tools several times and connect it each to another relay. For example, here like 4 relays. And then you can activate a contact on one relay and then go to the next screen and see if the respective binary input is high or not. So you can also check the cross wiring very, very easily here. Good. We can load data from the PC into the device. This is the device functionality upgrade. So if you need more function points in the relay, then you can use the SIPROTEC tools or the DXI. But if you don't have a DXI, use the SIPROTEC tools. You get this DAF file, and then you load it into the relay in a few seconds, and then you have more function points in the relay. If you have the device driver of the relay, you can upgrade the device firmware. And if you get a configuration from the DXI from someone, a so-called TCF file, you can also use the SIPROTEC tools to load this TCF file into the relay, so to change the configuration of the relay, basically. In the other way, you can get process data from the relay and store it on the PC, or also a configuration. You can read out a configuration from the relay, store it on the PC, and this then can be used in the office in the DXI5 for further analysis or whatever. Then we have the SIPROTEC digital twin. This is a virtual model of the SIPROTEC 5 devices running virtually in the cloud, basically. And here you can test your configuration with a virtual device. If you don't have the real device already here on your table, for example. I will explain more in the next webinar about this digital twin. If you're interested, here is the link. You can try this out. We have also a trial license for that. And again, in the next webinar, there is more about this digital twin. Finally, I would like to mention that we have a motor protection application guides for those who want to know more about SIPROTEC 5 motor protection. It's a booklet of about 80 pages, so you can download it here for free, of course. And here we have setting examples for the various motors and some basic explanation about motor protection. So with this slide, I would like to end. Let's come to the question and answer session. Thank you very much.
Okay, thank you, Klaus. That was
you're welcome.
great. A lot of information in there, and it was very positive to see while you were speaking that there were so many questions coming in. Just so that you know, as the audience, we received between 50 and 70 questions during this period. Klaus has already answered about 15 or 20 of them directly into the chat, and we'd like to address some of the others here that could be of interest when we're talking about this. Mm-hmm. One of the first questions that has come up, is it possible to use tools to simulate a motor starting sequence, that is to fine-tune the procedure before the final commissioning of the system? Klaus?
Yeah, this would be the digital twin. So with a digital twin, you can also replay an already recorded fault record, or you can also use sequences, which you can put on the relay and then see what is the reaction of the virtual device, basically, of the digital twin.
Okay, another question that we received from several sources. What would be the rating of a motor to have the requirement for 87M or for differential protection, and when is regular overcurrent protection enough?
Yeah, this is not so directly to be answered. Depends on how critical, how important the motor is, and how many money at the end someone would spend for the protection of this motor. 87N, the differential protection, of course, has a lot of advantages compared with the overcurrent protection. I think I explained that in the video. And for example, you are faster, you are more sensitive, and you need to invest something to get this function. Yeah? We have the two possibilities, as you saw, to make this differential protection. Guideline roughly is, or what we see is, for the smaller motors, normally just the overcurrent protection is used. For the big motors, differential protection is used. Now the question is, what is big and small? Again, this depends. So in my slides, I think I put a line, a limit of 1 megawatt maybe, but I don't remember exactly where it was. So it's up to how important the motor is, I would say.
Okay, we got a question from SMH, but I'm sure it came from a couple sources also. How about a recording of this webinar? We said we were recording, and how do you view that? Using the same registration portal that you used to participate for today, when a new participant registers, there will be a link generated to then watch this video or this webinar on demand. It will no longer be possible to ask questions or to participate in the chat and the information exchange that has been running during this video, but you can watch what has been recorded. There will also be a download link made available very shortly, where you can download this presentation that Klaus showed and some other guidelines and information about how to go through the process of creating a system with motor protection. Let's see. R asked us a question about input-output modules for Profinet or IO-Link. Klaus?
Yeah, we have a module for Profinet. IO-Link we don't have, but for Profinet. So it's basically an Ethernet module, and one of the protocols that run on this Ethernet module is Profinet IO.
Okay, we got a question. Will we share the slides at the end of the webinar? Yes, we have addressed that question. Mm-hmm. So let's move on to another one that was of interest. is there a function for recording electrical magnitudes, for example, during a startup?
Yeah, we have a special so-called startup recorder. This is also pre-configured already in the devices. And it records the currents, voltages if available, and some binary signals, the status of the motor. And it's triggered by the closing of the circuit breaker. But this is only as one dedicated configuration of our standard slow scan recorder functionality we have in all the SIPROTEC 5 relays. And they can record longer periods, so not only like the motor start normally up to, I don't know, a couple of minutes. This can be even longer. So for the motor starts, we have normally hundreds of these records in the device available. I think I mentioned also in the video. And this is basically the one to see the startup procedure.
Okay, we also got another question about the possibility to connect temperature and vibration sensors into the protection relays. Is that possible?
Yes, we have now for SIPROTEC 5 the Modbus client functionality. That means you can connect sensors, equipment via Modbus to the device, and the device will register these signals. For the temperatures as such, the 7SK82 provides a direct connection of temperature sensors like PT100, for example. For the others, we have at the moment a temperature box where you can connect these sensors, and they then are connected to the device via Ethernet. But it's planned also, it's already in development, to have also for the modular devices an expansion module where you directly can connect the temperature sensors.
Okay, thank you, Klaus. I saw another question that could be of interest here. What typical industries would probably have the most interest in a motor protection scenario like you have? And I'll take that question because I think that's one that probably addresses a wide spectrum of the people watching today. Typical industries for motor protection applications themselves are typically those industries with very large motors and very large loads. For example, the oil and gas, or the metals and mining, the chemical, pulp and paper industries, water, wastewater, and don't forget power generation with all of the actual loads inside of power generation plants. I'm sure there are many others, but if you are involved in these industries, then we probably have the solution right for you for motor requirements. Okay, Klaus, there was another one that came up. You pointed it out as it came in. The question was about what kind of SIPROTEC 5 requirements might there be for variable frequency drives, variable speed drives?
Or protection functions better. So with variable speed drives, it depends. Often variable speed drive has already motor protection functions inside, built in. So then you might not need, unfortunately, we must say, not need a protection device, a separate one. It depends if you just start up the motor with your VSD, and then you switch it on to the line. Then, of course, the motor protection comes in. So it depends. I would say check what the VSD has. If there are protection functions missing, then the protection device, SIPROTEC 5, the protection device, they can jump in. They are able to handle variable frequencies. So we have a frequency tracking functionality in there in all the devices. And with this is possible to trace the complete frequency spectrum. Okay, not 0 Hertz, but from a very low frequency starting.
Like I mentioned, we have a very, very large number of questions. We won't be able to address all of them today. What Klaus and I will do after this webinar is finished, we will go through and collect all of the questions and put some answers next to them and make that available for download afterwards as well, putting the questions and some short answers next to them to give you feedback and give all of you an opportunity to participate and benefit from the questions that all of you have offered. We'll do that now. Our time is running out now, so we'd like to at this point say thank you very much to all of you who joined us. We're very, very happy to welcome just about the entire world, from Mexico to Australia, and from Poland to Bahrain and Angola and everything in between. So it's a great event having you all with us today. We hope when you have questions, you will contact your local Siemens organizations, and you'll also find additional contact information at the end of Klaus's presentation.
Yeah, thank you very much for watching. Also from my side, it's really a great feeling to have people around the globe here watching. This is really great. Thanks a lot again.
Thank you and have a good day.